think all of you came to know that Professor Datta is as good as an experiment as is in theory. He could have given this talk, but I guess he's tired. So almost like a continuous, discussion. So this is a break, and this is really a kind of vast topic. So it's not possible to cover or even touch upon every aspect of mesoscopic experimental, because since 1988 there is a very active area of research, both in theory and experiment. So I have selected few, maybe biased with my personal choice. And second point is that some of you may know this thing, may be expert on this. So just tolerate me for some time if you know these things, and if you feel this is a repetition, but let us see. Okay. So and probably I will stress upon more on the low dimensional systems. Okay. See, let us start with a particle in a box. Let us start with a particle in a box. You know that for any bound state in quantum mechanics, you get a energy quantization, and these are the eigenvalues and the eigenfunction. Fine. But what is the simplest experiment you can think where you can, we know that you can make a quantum world using a $1 million instrument like molecular matrix C or MOCVD, and I'll discuss about a little bit of MD. But really interesting experiment reported, I think last year probably. Now take this molecule. Even I don't know what is the name of the molecule, so let us not worry about that. But the only thing is that this molecule doesn't have these two kind of groups. So when you add these two groups on top of this molecule, then it becomes a slightly different molecule and it becomes photoactive. Photoactive means if you shine light on this molecule, it gives back your light. Okay? Okay? Now what is the distance between these two groups? 8 angstrom. Now let us ask a question: what wavelength of light it will emit? Okay? So now you can just let us assume that this molecule, because of this physical barrier, behave like a quantum wave. Now you can calculate this what is the transition energy. It is h bar square, 8 by 8 ml square, that we know, but n1 square minus n2 square, this kind of final and initial. And if you put all these values, and you know there's energy eigenvalue depends on mass and the width of the wave, that we know, and it comes around this joule. Now if I convert this joule to the this thing wavelength, you get 700 nanometer, and if you do the experiment, it gives 680 nanometer. It's not bad. Okay, so this is the simplest way of now one can make a huge model why it gives like a particle in a box example. But what I'm trying to say that now nowadays there are many possibilities in the combination of different organic and inorganic molecules to represent or to show you kind of undergraduate kind of experiment where even I can give you a molecule where you can almost emulate the harmonic potential. Okay, and I know this first harmonic potential artificial was done in Bell Lab in sometime 1982, and till today that was the costliest experiment I know. But nowadays molecules are available where you can emulate this harmonic potential. It's not even a 10 rupees experiment, okay, at the cost of the molecule. So I think many quantum effects, mostly the closed systems, can be represented by novel experiment where you may not need a very high-tech experimental facility. Now, so what are the systems, what are the, means how physics is blessed with this mesoscopic phenomena? One is the quantum Hall effect. You know, normal Hall effect your Hall resistance or Hall voltage or whatever you call it, that's an independent variable. You plot along y-axis along the magnetic field, or if you keep the magnetic field constant, you vary the gate voltage. Okay, and you get a linear dependence like normal this sample if you do this experiment. But in 1990, when you do this thing in 2 dimension, not in 3 dimension, 2 dimension and low temperature, fairly good sample, okay, then you see that this is the, you get steps, and finally 6 RMW, like it was given on this, just on this one curve. And but the fact is, I want to emphasize here that this is a kind of 2D meso-nano phenomena, okay? You don't observe in 3D, okay? Second important milestone in physics and technology is the high temperature superconductivity. You can see that here I plotted the transition temperature versus the time, and the black ones, the color is blue for certain materials and black for certain materials. Now, this material, including the MgB2, which was probably discovered in only 2001, they are called, technically called low temperature superconductor. Actually, low temperature is not the correct term to use for it, because in MgB2 you can observe superconductivity at 40 K, even 42 K for certain cases, okay? And but these group of material can be explained with a theory called BCS theory or different flavor of BCS theory, okay? But this material, which are shown in blue color, they show kind of transition temperature which is higher than it was achieved till 1986, and though the problem remains unsolved, I think this is the greatest mystery in physics, what is the mechanism of superconductivity here. But all we know that whatever till now we know about the superconductivity cannot be applied in this material, number one. Number two, what you know, one experimental fact, that in all these materials, certain 2D copper oxide layer is responsible for superconductivity. Now, one thing is accepted, that if you want to observe the high temperature superconductivity, you have to play in 2D plane. Okay? So high temperature superconductivity cannot be observed, it's like a theorem almost, in a 3D system, number one. Number two is that oxygen, before that we thought that oxygen may be essential, but now different systems where oxygen is not there, non-oxide systems. But other thing what we consensus is, these are completely new physics, which is called strongly correlated physics. It's not like a block Mott physics. Till Mott shows that the completely different kind of physics can be involved if your electron-electron interaction with your system is stronger than any other energy scale. Okay, but point I want to emphasize here, you can observe this novel phenomena only in 2 dimension. Okay. Second is last 2 examples when you go from 3D to 2D. Now I want to give you one example where you go from 3D to 1D. Kind of spin church separation. Let us see, it's a slightly conceptual, but let me see what I can do. Now you take a kind of a spin in 1 dimension, and these spins are arranged antiferromagnetically. That means 1 up, 1 down. Okay, fine. Now what you do, you take out a spin. So you have a vacancy there. Okay, so you remove 1 electron, and that electron had down spin. So you have a vacancy. Now left side and right side of the vacancy you have a down spin, and let us apply a bias at the end. So kind of a positive charge that will try to move, okay, depending on the direction of the bias. Now, so the point is that this vacancy, if this is a negative terminal, they will try to go, and this is 1 dimension, so hopping is not allowed, so you can go only by exchange. When it exchange with the next one, only the down spin can go here, right? Because before that it was a down spin there. Now the problem comes. have in antiferromagnetic configuration, you have a two downspin next to each other, which is not allowed because this is an antiferromagnetic system. Okay, let us go further. Now it was before, now just reviewing the case. This is a downspin. If it goes here, the downspin will go here, and then further when it moves, then it's not a problem because it was an upspin, it will go, the upspin will be moved here, but further movement won't create any problem except there's a kind of point defect created here, two spins are down. So this Latinger first showed in the paper in long back, and finally this is called a spin-charge separation. So charge and spins are like a 2 degrees of freedom, and they are getting separated in one dimension. And I think last year it has been shown in carbon nanotube experimentally. So it's like a charge excitation and spin excitation. Now the thing is that the point I want to make it, this can be observed in 1D, 2D is controversial. That is not because 2D, half of the world says it exists in 2D, half of the world says it does not exist in 2D. 3D, you cannot observe this kind of, it's a forbidden for 3D. So the point is that when you go to lower dimension, it is easy to observe the different mesoscopic phenomena. Okay. So in what that means, in one dimension, antiferromagnetic electron is no longer exist in its form what we believe electron is. Okay. So it's like a spin in, then electron can be written as a superposition of two wave function. One is boson and one is spinon, and rest is all different model. Then this is discussed probably in the great length, that I'll just go quickly, that when you go from 3D to 1D, your conductance is inversely proportional to N. So till 88, we thought that you can get a superconductivity just making it L0, but unfortunately that doesn't happen because Professor Datta showed it's quite thoroughly that always G, the conductance actually, whatever the L becomes, conductance converge to a value 80 microsiemens, that is the 12.6 kilo ohm, the resistance. So this is also, I'll discuss the experiment, 1988 experiment. Though this is the beginning of mesoscopic physics, but in different directions of the condensed matter physics, if I think of any experiment has maximum probably effect or maximum kind of role, then this would have been, and the great surprise to me, I still don't know why these guys are not given Nobel Prize. One story I know that two papers came simultaneously. You cannot give Nobel Prize more than 3, but here all 5 were equally responsible. This could be the one of the reason. Okay, so I'll come back to this again. Third is that fourth example I want to give you. This is called scalmions. Okay, what is scalmions? Just let me explain a little bit on board. Now you know, suppose I have two spins, okay? In ferromagnet they are parallel, and antiferromagnet they are anti-parallel, okay? And we know that you need certain kind of interaction between spin for ferromagnetism and for antiferromagnetism. And what is that origin of that interaction? We know that's an exchange interaction, purely quantum origin. There is no classical analog of exchange interaction, okay? Now, so this magnetism can be divided into two parts. One is, let me call it ferromagnetism, and AFM, antiferromagnetism, and we can call it a isotropic. Okay, I'll explain why I call it isotropic. And the interaction is isotropic. So what you do, you can model this ferromagnetism and antiferromagnetism with a Hamiltonian, which can be written as J Si dot Sj. This is a famous Heisenberg Hamiltonian. Okay, and with this Hamiltonian, you can explain the most of the mechanism of ferromagnetism and antiferromagnetism. So, what are the mechanisms responsible for ferromagnetism or antiferromagnetism? Direct exchange, super exchange, RKKY, right? These are the three, and this can be explained, but unfortunately this cannot be solved 3 dimension. It can be solved in 2 dimension for nearest neighbor, that is Ising model, because this Ij can scan over the whole lattice. If you pick up only the nearest neighbor, then this model called Ising model, and 2 dimension, 1 dimension and 2 dimension, it can be solved exactly, but even the nearest neighbor is, you can get a Nobel Prize if you can solve it, okay? So that's, but we know that this Hamiltonian can explain this. But there is another material where this interaction can be anisotropic. And it can be thought of, suppose a Hamiltonian, this Hamiltonian based on the dot product of 2 vectors. You can think of why should we consider a cross product of 2 vectors, okay? And I'm quite surprised that it was not discussed in physics community till recently, till few years before. Scarmy first showed in certain problem in nuclear physics, and if we ask the question that instead of this, if we can write this Hamiltonian, write this way, Dij, and this Dij is a kind of a vector, let us assume for the time being vector, it's not exactly vector, it's a tensor, and then Si cross Sj. So this could be another interaction, another type of interaction. This is called DM interaction, DM Moria interaction, something called. Now, if you switch on this kind of interaction between 2 spin, you will see that you won't get ferromagnetism, you won't get antiferromagnetism, you will get this kind of so you'll get this kind of, this called topological spin texture in 2 dimensions. And it has been observed in certain material called MnSi, and I'll give you some experimental, MnSi, then iron, galvanium, and the most one is X, cobalt 1 minus X, and silicide. There also the heavy metal thin film. So there is a deeper connection between spin Hall effect and the these fermions, because fermions in metal thin film can be observed where you have a strong spin orbit interaction. Okay, for example, same metal, platinum and tantalum is their material is ideal for observing the fermions in metallic system. Okay, now this is slightly difficult to. So what happened that you can make out is, though it's a too simplified, it cannot be shown in 1D, but even if you see it, say at the end 2 end spins are up. So it's like that if you have this kind of structure, so fermions normally your ferromagnets will be like this. Now if you turn like this and make it, and this is the fermions, but this is not the end of the story, this is actually wrong. Now you have to then, like a graphene, like a carbon nanotube, you have to now close the loop, and that becomes a fermions. There are 2 phases of 2 different textures of fermions, because in addition to that there is another anisotropic term comes, and then you get this thing. Now why this fermions is becoming important? Except the beautiful physics here, this is the experimental observation of fermions by Lorentz microscopy. This is one way of observing using the transmission electron microscope, and let me just expand it, you can see it here also better. Okay, by different colors you can observe the spin texture on the surface of the material. Now this, in addition to the beautiful physics behind these fermions, these people think that this will be the ideal system for future memory devices. It has all the, there is something called figure of merit for different systems for memory. This has got the highest figure of merit, And already there is one paper in Nature, I think last week, they have shown most of the, not most, few logical operation using the memory built on the, based on this scandions, okay? Now, so all these systems, how we can make these systems? Now, there are different methods, but this is kind of a systems we encountered in condensed matter family. You start with atom, then you go to molecule, you go to condensed phase. There are two types of condensed phase: hard condensed phase and soft condensed phase. Metal semiconductor insulator, but in soft condensed phase you get liquids, molecular solids, and polymer. Okay, this is the way normally we make any condensed matter system. So suppose you want to go to mesosphase and or nanosphase. You have to break the rule somewhere, right? So where? Best way of doing, avoid going from molecule to condensed phase. If you take a detour kind of here, you always end up observing the certain meso and nanostructure. This is the broadly the kind of algorithm for experimentally getting the meso or nanostructure. Okay. So there, based on this, either you go from here or here, depending on the direction. There are two methods. One is called top-down method. Obviously, there will be bottom-up method. In top-down method, you go from bulk solid to single molecule and then single atom. So I'll give you some examples. Now, the best example is that because of this kind of phenomenal progress in the lithography, you can create microchip from the silicon wafer, and these are the intermediate steps. I think all of you know this intermediate step. Just I want to emphasize this is an ideal example of the top-down method. Okay. Now, what is the next method? Is that top-down method is the molecular beam epitaxy. You take a ultra-high vacuum chamber, and then you get this material in gaseous state and eject this. Then atomic, you can get it in ionic state, and you release this atoms or ions by opening the shutter, and because it's a high vacuum, so their mean free path will be more than this distance, so they will come and sit where you want them to sit. And that is the whole idea of why you have to have a ultra high vacuum. If you have ultra high vacuum, their mean free path is almost like this is the chamber which is typically with this 1 meter, but kind of 10 to the minus 11 torr, the mean free path is 10 meters for most of these atoms. So there is no problem. You have to make sure that when the atom is coming from here to here, they are not diverted because of the scattering. That's all you have to take care. Okay. So and pressure is just what background pressure should be. That is decided by this fact. Okay. So this is another way of making the top down. You can get, of course, 2D system, 1D system, and 0D system by this method. I'll come back to this method a little bit more. So another top-down method is the mechanical exploration of the graphene from graphite. I think all of you know that. I'm not spending time here, but this is another method. But it need not be only by the Scotch tape. Nowadays, it can be done by the liquid exfoliation and many other ways of getting the graphene. Okay. Now, let me give you some examples of the bottom-up method. In bottom-up method, we start from the atom, then we go to molecule, and then bulk solid. Okay? So this is an example by which you can make the gold nanoparticle. This can be, I think, introduced in the school level experiment also. So you take this gold compound and you heat it at 300 degrees centigrade and put some reducing agent. Okay? And you will see that depending on the certain, like a capping agent, you get a different size of gold nanoparticle. Okay? And then finally from the plasma resonance, you can ensure that you got the nanoparticle. Not only that, you get a fairly good idea of the size of the nanoparticle. This is the TM picture, and you can make out this is roughly 7-8 nanometer width, and this is a kind of a kinetics of the system, how you get it. Okay? There's another method is developed by Biondi in MIT, First, he showed that using these two very simple materials which are known, you can get indium arsenide quantum dot or cadmium selenide quantum dot using the very simple reaction. But look at the reason because all of you know this method, but one thing I want to look at the TM picture. This is the near perfect lattice. So what I'm saying that these methods are near equilibrium method. You know that in any crystal growth is a non-equilibrium process, but always our attempt that to grow the systems near equilibrium. By that you can avoid different phases, you can reduce the number of defects. So till today, this is the best TM picture I have ever seen for any nanoparticle. Okay, look at the, you can expand it and you can, with your eyes, you can see that there is no defect here, almost. Okay, the other bottom-up method is quite popular. Now, it was very popular 5 years before, creating a nanostructure using the STM. So what do? You take the metal tip, bias it, so that, and dip it in a liquid where you have ions. Depending on the biasing, what polarity, it will attract the positive ion and negative ion. So then you move these ions will stick to the tips, and then you move these tips, and then you release the bias. This way you can make a nanostructure almost made out of only 10 atoms. This is a method, the only method by which you can make the smallest nanoparticle or smallest nanostructure. An advantage is that not only you can create a nanostructure, you can move the atom and put the atom wherever you want. Okay? Different groups in IBM almost perfected this technique, and there are several papers on this. Another bottom-up method for growing the graphene is the epitaxial method of graphene from silicon carbide. What you do, it's not a very complicated method. You take silicon carbide and heat it. Carbon is lighter than silicon, so they kind of inside solid sublimation happens, and carbon comes up on the surface and it tries to find out the minimum energy configuration, and then it obviously graphene is one of the minimum energy configuration or the minimum energy configuration, a little bit of correlation, and then they get a beautiful monolayer. So this is the bottom-up method for growing the graphene on substrate. Another method, bottom-up method, for example, I want this kind of structure, a molecule between two metal electrodes. And molecule is there in kind of solvent. You can think of any molecule, including protein, DNA, kind of big molecules, or even the smallest, I'll show you, not show you, I'll just give you the first page of the Nature paper where they have measured the conductance of a single hydrogen molecule. So this could be a hydrogen molecule also, okay? Now how you can make this kind of structure? It based on the self-assembled monolayer developed by Whitesides in Harvard. There's a beautiful Scientific American, this is taken from their article. So what you do, you take a kind of a solution, okay, solvent could be chloroform, could be methanol, anything, and you put the molecule, the desired molecule there, the molecule you want to make a nanostructure out of it, okay, and then you get another silicon substrate, coat with gold, but if before gold, if you put a layer of titanium, it will be better. That will reduce the surface energy of the silicon. And then you do a little bit of flame annealing of the gold top layer. Flame annealing will make the gold smoother, okay? Because when you make a nano gold thin film, by any of the evaporation technique, you get a slightly rough surface. And then you do a flame annealing of the gold. It's very simple. You can take a even I think by candle you can do the flame annealing. That's not a problem. And then you put that substrate in the solution, just keep it for 12 hours, you will see just one and only one monolayer forms on the gold surface. Okay? And this is the STM picture of that monolayer. You can say it's a beautiful picture. This will cost you probably $1, but same structure, if you want to make it by the MB, you need it almost close to $2 million. Okay? And also this is a near equilibrium method, so density of the defect faces are much better here than your MB layers. Okay? So how do you characterize these monolayers? There are two techniques, there are many techniques, but the most two popular techniques are the scanning tunneling microscope. So you can get a surface morphology, and from here you can make out that only monolayer is there. Okay? Other method is that you have to find out the signature, like a fingerprint of the molecules, which you are putting on the substrate. So for that is the reflection absorption infrared spectroscopy. What is done here, you put an infrared light here and see the what are the wave numbers absent there. From there you can make out those are the lights absorbed by the molecule, right? So here I want to show you one thing, that here this molecule, you make a monolayer on gold and silver. Now it is known, it is theoretically predicted, and it is also experimentally true, that the gold, like a gold, on gold, this molecule are like a particle, okay? But on silver, it's like a horizontal. So obviously certain vibrational modes will be absent on the silver because there's your degrees of freedoms are less in the silver than the gold, and you can comparing by this IR spectra, you can make out. For example, this, you see that these particular vibrational modes are absent on gold, but it is on the gold, but not on the silver. The reason is that is the wagging mode of the horizontal topology of the molecule. So this is the way you can get the signature of molecule. So we know how to put molecule on metal surface. Platinum and gold the favored choice for obvious reason. But now how to put this molecule between two metal electrodes. Now, so finally our goal is to make this kind of structure. This many methods developed last 20 years. Nanopore, cross-air, STM, scanning probe, electromigration, nanocluster, and mechanical break junction. It's not possible to cover all. So what I will do, I will just explain, I will just spend probably a couple of minutes on nanopore and electromigration and mechanical break junction, because these are the most popular methods for making this kind of sample. So first is mechanical break junction. This is pioneered by a group in Yale. So what you do, you take, I think I need to draw this. So I'm not good at three-dimensional figure on PPT. So what you do, you take a kind of silicon oxide and then silicon, and you make a structure on that. Now what this structure would be, let me take a horizontal view. Structure is like this. You can see that it's so this is the structure. So what you do, you remove some portion of the SiO2 by reactive energy from here. So that means there is a nothing below this constricted portion, okay? And then what you do, you suppose this is your structure, and then you try to bend it. When you bend it, you'll get a break here. Depending on the bending, you can control the gap between the break, okay? Gap between the two sides of this structure, and then you put this solution, or rather you make a chip with 10 by 10 kind of matrix with this kind of structure and put it in the solution. And molecule, whenever molecule finds a kind of a compatible size, it locks. But in mechanical break junction, there is a little bit controversy. That's why people are nowadays not using the mechanical break junction, because some of the experiments could not be repeated. This is the first experiment. How it is done? It is not the way what I said. It is mechanical break junction made this way, but what they did, they put the molecule on both sides of the contact, and then again they tried to reduce the curvature so that there a molecule-molecule junction again reform. So that is the difference. But this created a lot of controversy, and people say that it is quite a. So actually there is a end-to-end molecule connect. Reproducibility is the biggest kind of casualty here. So the thing is that, but whatever it is, they show that when you put this kind of molecule, you get this kind. This is the first clean IV characteristics of a single molecule. Okay, and when you take a DIDV, you can get the kind of a from DIDV you can get a gap in this molecule in their electronic structure, which is not exactly homo-LUMO gap, but this is a single molecule. U is very large because you know that Hubbard U, or rather electron-electron interaction, U depend inversely proportional to the size, so U will be very large for this system, so you get a gap plus U in this case. Okay. So the same group also developed a nanopore. Now, how nanopore was developed? You take instead of silicon oxide, you take silicon nitride grown by LPCVD on silicon, and then you create a window here by reactive ion etching. Okay, is clear? And then through KOH, you etch the silicon from this window, and then your top silicon nitride layer is hanging on this kind of notch, and then you make a hole here using E-beam lithography. So there are 4 steps. Take silicon, cover silicon nitride both sides with one of the CVD. They have used LPCVD, you can use any CVD actually. And then create a window. Silicon nitride can be etched by reactive ion etching. So create a window. Through that window, you let KOH. KOH will etch out this portion of the silicon. So KOH etching will stop till it hits the top silicon nitride layer, because KOH cannot etch silicon nitride. This the reason we have taken silicon nitride here, because it's silicon oxide, KOH also etch out the silicon oxide. And then you stop here, and then you create a hole here. That way you can create a nanopore. Okay. Now this is the ACM picture of nanopore from the same group. And so once you create a nanopore, then you put you put a first. Next 3 steps are important. So you have a nanopore, put top electrode, and then you put molecules by same method, self-acid monolayer. By after putting the molecule, and then again you put gold electrode. Now there is a doubt whether the second evaporation destroys the molecule or not. So there is again this method subjected by this kind of scrutiny. Now when you they put this kind of molecule, okay, they get NDR at 60K. And you know, everyone looks for this kind of IV characteristic. As soon as you get this, everyone jumps that this will be the future memory device, storage device, and all those things. So this work was followed by flooded of parallel activities. Though the exact mechanism is still not known, because I think Professor Datta's group got an NDR without this group also, right? In your PRL paper, you don't need this NO2 and NH2 group to observe this.
So striking is how big that
yes.
jump is. I'm not sure, but nowadays isn't the understanding that there were actually pinhole shots or things like that?
Yeah. Now say that's what I said, that pinhole shot comes because of the second gold evaporation. That's what I said, that this nanopore is a little doubtful because you know when you make the second layer, it easily gold kind of filament can form between top electrode and bottom electrode. Okay. So, and there is an electromigration which is long before shown that this metal filament can act as an on-off switch, and this is reproducible. And that's why thousands of paper you have seen that recently they call a registered memory based on oxides. They based on this metal filament because you have a metal filament, you apply a bias, certain threshold bias, the break. When you remove the bias, they rejoin and you get back kind of your on and off current. So people think that that is the, but whatever it is, one thing we have to give credit that this is the first paper where they even not only this, there's several other things they developed for the first time. Okay. So anyhow, as I said that there is a controversy regarding its mechanism. There is a controversy regarding its whether the conduction at all to the molecular is there any parallel channel exists. Anyhow, so this is the historically the first organic nano switch. The electrical break junction. What is done here? You take a metal film. You can put a notch here, and then when you pass a current, and then beyond certain threshold voltage, though these are current limited, but it's fine. At threshold voltage, you get a break. This is like a fuse. Nowadays, we don't use fuse. It's also switch breaker. But previously, switch breaker was not there. There used to be a fuse of certain. So suppose this circuit carries a 5 ampere, should carry a 5 ampere maximum. We used to give a fuse with a 5 ampere. So if it crosses 5 ampere, it will melt and fuse will be broken. The same idea was used. The good thing about it that you can create a kind of a gap which is beyond the scope of present day best of the best lithography technique, not even by the X-ray lithography. Okay, so you can go down. This is other FESA picture. You can make out from here that this kind of gap is less than 5 nanometer. Okay, it's not very easy to make a lithography defined 5 nanometer or even 4 nanometer gap. But by this method, very easily you can create. Even people have created. I know one group in Cornell, they have created almost close to 1.5 nanometer by this technique. Okay, so now you plot the conductance versus distance. So from the quaternary current. Okay, you can do that, and you will see that when the gap is in this region, they exactly matches with the width of the molecule. That means if I get a conductance gap of if I get a conductance of this, and that is a kind of indirect hint, and put it in below FESM, and because FESM you cannot see anything below 5 nanometer, but typically molecule is 1 to 2 nanometer. So what do? You first check with this conductance. From this conductance, you estimate the gap and then see whether it is less than 5 nanometer. And then you select those chips where you have a less than 5 nanometer gap. Okay? And then put it this molecule, and you can get IV characteristics for this. You can get a IV characteristics to single molecule, but there is a doubt how you know that there is a single molecule or there are 10 parallel molecules. So from the distribution, this is a so on a chip you should make at least 50 devices, or I would say as many as devices possible, and then take a statistics and think of a kind of a Millikan oil drops experiment. You will see there is a distribution of this resistance you calculate from the linear region, and there is a, for example, here I show that this is a 200 kilo and there is a 10 mega. Okay, so there is a wide variation of the conductance of this gap. So one can conclude that when it is a very high resistance, there must be 1 or 2 molecules. Okay, and when it's a low, then it must be 10 molecules because it's a parallel channel. Okay, so you do, and the second experiment, what you do, you just increase the size of the molecule by putting CH2 group here. And you can see that immediately it was 200 kilo ohm and it became 20 mega ohm, and it was before 10 mega ohm, it became 26 mega ohm. So what you do, and then you take a kind of a Millikan-Noel-Dobbs kind of experiment. You divide all the characteristics by certain integer. When they collapse only one, that must be due to single molecule. Okay. So this is the way one measures the resistance of a single molecule and also current transport through a single molecule. So from this exercise, the resistance of this molecule, where you have two extra CH2 group, is 26 mega ohm. And for this molecule, where there is no CH2 group, that is a 10 mega ohm. From here, you can get a rough estimate what is the resistance of a single CH2 group. And that comes around 8 mega ohm. Obviously, it will be much higher than the 12.6 kilo ohm. So this is the way you can put different molecules and measure their resistance. Not only that, you can think of very novel experiment by you can create an asymmetry in this molecule, and from you will see that if there is asymmetry in the molecule, that will be reflected in your IV characteristics, and you can study many other different things. And though this is the domain of mesoscopic thing, but according to me, this could be the kind of a ideal system to study the electron-electron interaction in the system. So always I found that two experiments in mesoscopic system. I'm just coming to point. Let me finish this sentence. Two experiments in mesoscopic domain was is always accepted, but there is no kind of a direct proof. One morning that was the kind of the chemical potential in the diffusive conductor. I didn't know before that this spin Hall effect. You can measure the mu plus and mu minus separately. That was one. And second is the what is the quantitative kind of role or quantitative effect of the electron-electron interaction in small system, because these are the ideal, because you know that simple back of the envelope calculation shows that as you reduce the size of the system, your electron-electron interaction. This is simple. Suppose I have a big system. So if I take out the electron from there, how much energy I have to spend? En minus En minus 1. Now this energy depends on the size of the system. So if I reduce the size, then this energy will be much higher. So these are the system will be ideal. I think this is, I don't know why people don't study here, but according to this, because electron-electron interaction is you cannot study from the momentum relaxation kind of experiments. Okay, so so these would be the ideal system for studying the several, even many body interaction, though it's a single molecule case. But people thought that okay, they will do it as a metal nanoparticle, but till today we don't know how to address one single metal or semiconductor nanoparticle. So probably molecule is replaced by some metal. Yes.
Sir, with this electromigration direction, can
Yeah.
you study the tunneling current? Does the tunneling current between the molecule and the contact before attaching?
Yes. From the tunneling current, we estimate the gap. You know this exponential by d, right? So from there d, what you can get from the WKB approximation very easily, there is exponential dependence, right? From there we calculate. This is the one. Yeah, this is the one we have estimated from the WKB approximation of the tunneling gap. So if the gap is more, you can see that if the if the gap is more, your conductance is less, and this is a similar plot because it has exponential dependence. Okay. And so next is the quantum web. This is more like a zero-dimensional system. Now, how this is the quantum point contact experiment based on quantum web. Now, you know, quantum web can be fabricated in the lab two different ways. First is that you can create a quantum web, and that's not very difficult by MB. What you do, you suppose you have a gallium arsenide layer. This is your gallium arsenide layer. So you, by some lithography, before that people used to use sophisticated e-beam lithography or photolithography. But I can tell you a very simple technique, and by which you can create a kind of a well-directed nanowire in the lab. So what you do, you take a STM or AFM, tip on that and scratch that. This is one way of doing it. And then you will have a notch here. So if I take this is the top view, side view would be something like this. Side view will be something like this, and then you grow the material. So you'll get a triangular kind of shape nanowire. These are the, because like a beam directed or randomly directed nanowire is not good for the device, because you don't know where to make a contact and how many nanowires are there. Suppose you want to make a single device from nanowire, and you know that carbon nanotube nanowire did not take us anywhere. So carbon nanotube is well directed, but it has, like a graphene, it has all the disadvantages and the advantage. So, but I personally feel still good old 3.5 and 2.6 nanowires will be the solution for future nanowire based devices. So this is one way of making a nanowire. But electrostatically you can make a nanowire also. So that is done here, and I will spend a couple of minutes on that. So you take a 2D electron gas between gallium arsenide and aluminum gallium arsenide. Okay, and top you put two gates, and I'll come back this figure there. But let me see first how I'll make 2D. So as I said that you take gallium aluminum arsenide. This is a technically called diffusion cell. There is nothing but a metallic chamber where you have this metal either in liquid state or solid state, and you hit this chamber more than the melting point. Typically 200 degrees centigrade more than the melting point of that particular solid. Okay. Keep the system overnight. Go to vacuum 10 to the power minus 11 is better, but at least 10 to the power minus 10. And then, see, I have experience on silicon germanium MB. That's much more difficult than 3.5 MB. Silicon germanium MB, you won't get anything if this vacuum is anything less than 10 to the power minus 11. For gallium arsenide, indium phosphide, indium arsenide MB, you can manage it 10 to the power minus 10. But not with silicon germanium. So then what you do, you take gallium arsenide substrate, okay, and you rotate the substrate. Rotation gives you a little better information, okay. So now I will open this for certain time, and this time is not like a microsecond or millisecond. You can, for one monolayer, you can keep the open for 10 seconds, because if it is a microsecond, it's very deep, you don't know when you opened it and when you closed it, okay? So you have to adjust this particular angle and vacuum such a way that for one monolayer, you'll be allowed to keep the open this shutter at least for 10 seconds. Even for certain configuration, you can keep open for 1 minute. You'll get still one monolayer. Okay? So one monolayer I got. Now this monolayer is gallium arsenide, where for growing gallium arsenide, I opened gallium and arsenic. Now I want gallium and aluminum arsenide. Now I'll open 3 simultaneously, and I'll get gallium and aluminum arsenide. This way you can make layer by layer group. Okay? So, and for 2 layers, if I need a 2D layer for my other experiment, so either I will use 2 layers or 3 layers, either triangular well or the rectangular well. But mostly triangular well is good enough for this purpose. Okay. But let me tell you, by this method, you can have a time, or if you have interest, I can explain it. You can even make a quantum dot using this quantum dot by MB is a little tricky. You have to use kind of a self-organized criticality for quantum dot. Okay, so you make this. So your bottom is like a 2D layer, and then when you put a gate on top of it, as Professor Datta explained, these 2 papers simultaneously, they show that the conductance is no longer linear, with get voltage, but you get a steps. But let me tell you, but this is not a 2D effect. This is a purely 1D effect. So how do you get a 1D here? As far as I know, this kind of geometrical, not electrostatic, geometrical nanowire has not produced this kind of steps yet as cleanly as observing electrostatically created nanowire. Okay? So what you do, this is your gallium arsenide and aluminum gallium arsenide, and this is gallium arsenide. Okay? But you know that gallium arsenide, I have to put a gate. But in silicon, life is easier. You put a silicon oxide and put a gate. But gallium arsenide, you know, MOSFET is not possible. So you have to create a MESFET kind of structure. So you have to create a Schottky diode kind of thing. So when you put a metal, so you have a 2D layer. So metal, you know, this metal, when they are reverse bias, your depletion region will be like this. By controlling the bias, you can control the reverse bias like this. But when really it's a high reverse bias, you have a depletion region like this. So though actually the physical width of the 2D is this, by putting this electrostatic gate, you can create a constriction, and that's the way you create nanowire. And this is quite a popular technique nowadays. So how do you get this? So let us see. Typically the width is 250 nanometer between these two gates. Now I can vary this width, this 250 nanometer, but I can vary this width by varying the biasing on the, okay? This is not a transistor configuration, this is more or less for all practical purposes, this is Schottky diodes, two Schottky diodes, okay? So now for certain width, I can think of for example, when it is 100 nanometer. So it's a 100 nanometer quantum wire, energy will be quantized, okay? And how many eigenstate will be there will depend on the width, right? Now, so what do? I make the bias one here and one here, as Professor Datta said, this is a left and right. So how many channels will take part? 1, 2, 3 channels. So M will be 3. So I'll get these steps. Now I'll increase my reverse bias further. If you increase the reverse bias further, what you do? You are reducing the width of your quantum well. Now in the same with the same difference of the bias or the same difference of chemical potential, you have only two channels. So you'll get a 2. This is the way you can get 1, and this is what you are doing by this technique is nothing but you are playing with the width of the quantum well, and you know only one parameter responsible for how many eigenstates in mesoscopic language, how many channels or how many modes will depend on the width of the quantum well. So all you have to do, how to vary the width electrostatically. Okay, and now mu L and mu R will decide how many, within that difference, how many channels I have. If I have only one channel, I'll get this step. If I have only 2 channels, I'll get this step. So this is the famous experiment.
So,
yeah.
the separation of level you have kept constant. So is it just for illustration or is it experimental?
This is just illustration.
And from this
But-
also the step will get.
But the point is that this width also will increase with the inversely proportional to the width, the delta E.
Yes, so but from gate voltage, we have seen that same gate voltage approximately is for every step change.
This change?
This width of
Yeah, but the point is that that's what I have not shown the derivation. This energy dependence is somewhat so slow that you can take out of integral. So what you do, the derivation I should have. So actually what you do Fermi and then ME, this is 2E by H will come and then E, right? So this you can take a constant and you'll get 2E by H, FE, DE, this is your M, and this will give you at low temperature 1 and then you get. So the point is that that energy difference is not reflected in your number of channels calculation. Okay. So then this was done in 1988 and 2002. The Marcus group in this Harvard University, they show that this is not even a 1 actually. Actually they are 0.7. This is called 0.7 structure. And it's a very interesting physics is there. Though I don't think this is settled completely, but they show that actually point contact is nothing but is a Kondo Kondo structure. It's called isolated Kondo structure. So you have an electron which is floating inside the gap and 2 electrons at the 2 sides. They create a Kondo cloud, and that Kondo cloud is responsible 0.7 structure. And what is the proof? Because subsequent publication they show that the isolated Kondo effect anomalous temperature difference. This is again another signature of the Kondo effect. You see that as you increase the temperature, your mesoscopic effects are getting washed out, but your Kondo this structure is getting pronounced. This complete anomaly. Then what about the low temperature effects we study? You see that red, which is 4.1 K, and 0.08 K, which is this blue, or what is this color? Anyhow, whatever it is. So you see that as you go to lower temperature, your mesoscopic this steps due to this channel conduction is getting pronounced. But Kondo effect is getting washed out, and Kondo effect becomes more pronounced as you go to high temperature. And that they also did it using the magnetic field also. You see that at high magnetic field, these are equivalent, one can show. At high magnetic field, your Kondo effect is pronounced, but low magnetic field, your mesoscopic effect is pronounced. These two signature somehow supports the kind of a model that this is a kind of a isolated Kondo, isolated, they have given a name, I'm forgetting, they call it a, this is like a Kondo in a closed system, Kondo effect in a closed system, not in open system, okay? Then next experiment, this was 88, and then it took a long time to observe this mesoscopic phenomena or conductance quantization in metal. The reason is that Fermi wavelength in metal is really low, and because of that, but finally this Japanese group in this paper, this is another beautiful paper, they show that one can indeed observe this conductance quantization in metallic nanowire. But getting a 0.9 metallic nanowire, because whenever they used to pass a current, again the fusing effect used to happen, and this, every time you populate the channels, you have to make sure that your channel does not get affected because of this current increase. So that's why the reason probably it took almost 10 years to observe this in metallic nanowire, okay? But this is a very clean experiment. Then in 2002, they observed this kind of conductance measurement in the hydrogen molecule. You see that the conductance is close to 1. But it's such a difficult experiment that even it is much less than 1, but is accepted in nature. So one knows. And how you are sure that hydrogen molecule is there? When you take a second derivative of the conductance, that there is a very nice argument that gives you the molecular vibrational level. And that's the way, when they take a DGDV, they get this vibrational modes. These modes are neither for metal, not for contact, but for the wedge bonds. Okay? From this, they prove that whatever current is flowing from one electrode to another electrode is through the hydrogen molecule. Because I think I have some papers. The first paper in 1966, they show in a mesoscopic, this is a 3D paper, they show that when there is a transport for elastic, if it is an inelastic transport, one can, from the second derivative of the IP, one can get a vibrational modes of the molecule. And they typically use this, this was also finally shown by again that Yale group, that indeed one can get a molecular signature from the current transport from the second derivative, and that nature people use this, this signature. And then finally, condensed conductance in graphene, they took a kind of a suspended graphene, and I don't know, this is the nature physics, that's why it's a clean, I don't know, I thought for just a sake of completeness I'll show you the data, but this is a really poor data for this suspended for some other reason. One need a lot of imagination that this is the 1, this is 2, and then this could be 3, and beyond that there is nothing. So anyhow, but this is a historically first paper on quantized conductance in graphene, and that too suspended graphene, okay? And I can explain you how to make this sample if you have interest. It's not very difficult, you can make the sample, okay? And finally, this is one of my favorite papers, the universal thermal conductance or mesoscopic thermal. This paper, they show that what Professor Datta used the same equation one can use for thermal and transport also. And then finally, instead of familiar distribution, one has to use the Bose-Einstein distribution. But this has many other interesting features. And I would request all of you to go through a beautiful nature paper. I'll give you the reference. And then this paper, this Regu and Kirchner, they show that there is a universal thermal conductance as you have for the electrical conductance. But this sigma also depends directly proportional to number of channels, but is directly proportional to temperature. It's a order of magnitude difficult experiment than the electrical counterpart, okay? But this group in Caltech, they are a master in this. They made this structure, and the main problem, you know, why it is so difficult? Because in case in phonons are bosons, so you can't use the electrostatic constriction for creating the wire. So you have to physically create suspended wire through which the phonon, quantum of phonon will pass through. Michael Hughes was visiting here, and he told me that it took more than a year to make their first sample with that kind of facility. It's a really difficult experiment. So this is given all the reservoir, thermal reservoir. But finally, this figure you should look at. You can. This is actually the wire, and this is one left and right thermal reservoir. And then when they measured the thermal conductance versus temperature, they got 1. But 2 is not possible because you know it gets it's a deep populated. It's a both, they follow the both statistics, so it's difficult to get a other channel. But this is a beautiful paper. I would stop. Many of you may go through it, but this is one of the classic experiment after 1988. According to me. Finally, this paper 2015, which came, and here it is shown that quantized conductance through a single atom. Okay. Now, this is also a very novel experiment. Now, you know, single atom, you cannot make a contact. So what they use the atomic trap to trap a molecule, atom. This is the atomic trap, okay? And then finally, they pass the current and they observe the 1, 2, 3 the steps due to conductance quantization because of conductance quantization through the atom. And these are the different frequency. You know, atomic trap depends on the two perpendicular frequency you have to apply, and their resonance point, atom gets trapped. And you can see that for this frequency, you get a cleaner steps compared to this frequency. That means in this frequency, atom trap, there are a lot of, it's not a very, not a clean trap. So the cleanliness of the trap depends on the resonance frequency. Varying the resonance frequency is not very easy in atomic trap. And this, they observed that very clean experiment and that conductance quantization through a single atom. So I don't know, next will be single electron, single positron to the conductance quantization. Anyway, I think I should stop here. I should stop. Thank you. I can take few questions, otherwise I'll request Professor Dr. Is there any other question? Yes, tell me.
The electromagnetic break junction, what is the rate of reproducibility? Because the electromagnetic distance, every time it will change.
I did not get it.
The electromagnetic break junction you mentioned.
Yeah.
So the reproducibility is a big factor.
Electromagnetic radiation? Yeah. I can tell you this. In this business, you can't expect that the yield will be 100%. So what is done? Sorry, let me switch it off. Yeah. What is done? You don't make a single device. Okay. You make a kind of a array of devices, 10 by 10, 100 device on single wafer or single chip, and then create break junction in all of them. Typical yield is 10%. If you do things properly, if you have a good experimental hand, you will get 10 to 20% yield. And if you get a 20 devices out of 100 devices with a good reproducible break junction, I don't know, for some reason, 50% always will get less than 5 nanometers.
Sir, what is the typical width will be used for this?
Okay. I'll give you all the range. So ideally, not ideally, practically, you should take this structure, okay? Now this, lithographically you can't create this kind of, so if you blow it up, you will see that always it will be like this, okay? So if you use photolithography, then make it 1 micron. You can make it 2 micron also. And this 100 to 200 micron. And this length, whatever, this length depends on how many devices you want to put on a single chip. But make sure this is not more than 2 micron.
Okay, so even if it's 1 micron, you can get a gap as less than 5 nanometer.
Less than 5 nanometer. So the thing is that more, this is, if it is a 500 nanometer, you will have a probability of getting more less than 5 nanometer devices. Yeah.
So in electrical break junction, can we get the break junction for all the metals, or it depends on the melting point of the metal?
See, electromigration is quite a well-developed like subject in metallurgy. Electromigration generally is good for the metals which has a very high ductile ability. Ductile property, you know, that for example, aluminium is very bad for that. You can make, how do you know that metal is having high ductile property? If you get a thinnest ware, like for the gold and platinum. So obvious choice will be gold and platinum. Not copper, not aluminium, not cobalt. Nickel is okay. Best to be platinum, but you can't afford platinum. So next is gold. If you can't afford gold, you should try nickel.
It doesn't depend on the melting point of the
It depends on the melting point, but the point is that one can show that it is not a thermodynamic phenomenon. It's more like a kinetic phenomenon. So the thing is the melting point has secondary role. It all depends on how electric field moves the atoms. Okay, so that is more important than the thermal this thing effect on this particular atom movements. So it depends, but for example, platinum is very high melting point, but still you get a very good junction, very good this thing, as good as gold. So that shows that there is a difference of 2000 degrees centigrade between melting point of gold and platinum, but still you get the identical break junction. So that shows that the thermodynamics is not that important. Yeah.
So if you get a conductor quantization plot, so like you said, in atoms you are getting, in molecules you are getting. Basically the conductor quanta is already fixed. So what information does it reveal regarding the material? If you change
This
the
atom, I don't know.
just now you told
So
about
I don't know. This is done in the lithium atom. This experiment, because lithium, you know, this atomic trap based on the Bose-Einstein statistics. So you have to find out a particular spin state of lithium atom, and then so cooling of the atom is very easy, and that cooling is easy if they are bosons, right, instead of fermions. So the point is that right now the choice dictated by for the atoms for which one can trap easily. Okay, but according to me, the Landau theory says that you will get a T which is irrespective of the system. It does not depend on the system. So I would assume that for atoms and molecules it should be same. I don't know why the molecules they got a less than 1, because it's a difficult experiment. One can understand that. But I would assume that it should not depend on the system.
then physically there is no point in doing in different materials. Like
No, they have not done different. They are
no, in
different.
molecules also. I have seen in benzene and that kind of organic compounds they have
No,
done.
no, yeah, but you know, this initially lithography was not that developed, so they used to pick up the little bigger molecule. Now it's slightly advanced, so they can dare to go for the smaller object, like a molecule, like atom. Okay, so I think we need to change the. Yeah, 150. Oh, so lunch. Okay. So then we'll break for the lunch, and then first we'll start with Professor Datta's one small epilogue, kind of half an hour, and then that will be followed by discussion, and yeah, that's the plan. So let us break for the lunch. So we should come back here at 2:30. Okay.